Hi students, Professor Nugent here. In this video, we are going to discuss the variances of the OLS estimators. When we're thinking about the variances of the OLS estimators, we want to ask how far can we expect our estimate, beta 1 hat, to be from the true population parameter, beta 1, on average. To come up with an expression that is something that we can work with for the variance of the OLS estimator, we're going to bring in an additional assumption that is a very strong assumption. It's a bit unrealistic, and this assumption, it's not needed to prove that OLS is unbiased. It's only needed to simplify this analysis in terms of coming up with an expression for variance. We really don't even need it to estimate the variance because we can estimate the variances in a different way. We only need it to come up with an expression for the variance. Now, this assumption is homoscedasticity. What is homoscedasticity? It is the scenario where the variance of the conditional variance of u given x is constant. If we look at a plot of data, that means that over the domain of x, the observations or the errors over the domain of x do not, or the spread of the errors do not, does not vary. All right, the spread of the errors is constant. And that's what you see here. The spread of the errors is quite constant over the domain of x. When we think about the counterpart to homoscedasticity is heteroscedasticity, and that is the more likely case with economic data, and that might be where you have an increasing spread of data over the domain of x. All right, so typically we're going to work with data that demonstrates heteroscedasticity, and we're going to use heteroscedastic robust standard errors. But we're going to assume, in this case, homoscedasticity in order to come up with some nice expressions for the variances of the OLS estimators. Again, this is not needed to prove that OLS is unbiased. This is not needed for any other reason, just to simplify this analysis. All right, so if we have homoscedastic errors, and the variance of u given x is sigma squared. Now, the variance of u given x is the expected value of u squared given x minus the square of the expected value of u given x. But the expected value of u given x by the zero conditional mean assumption is 0, so this term drops out. Expected value of u squared given x, this is our variance, which is sigma squared. All right, so this is also our unconditional variance. So sigma squared is the error variance. Sigma is the standard deviation of the error. All right, so given this framework, let's come up with some expressions for the variances of our estimators. We're going to start with our expression for beta 1 hat as a function of beta 1 plus this additional term 1 over total sum of squares of x plus the sum from I equals 1 to n of di ui, where di, recall that di is xi minus x bar. And the variance, okay, so we're starting with this, and I want to take into account a couple of things. Beta 1 is a constant, right? Because this is a population parameter, so that's a constant. The xi are assumed non-random, right? We're assuming that the xi are fixed and repeated samples. So we're sort of taking fixed values of the x, which is analogous to random sampling. So the xi are assumed non-random. And the ui are independent random variables across the I. So the variance is the sum of the variances. All right, so the variance of the error is the sum of the variances of the individual random variables. All right. So variance of beta 1 hat. This is equal to variance of this whole thing, right? We plug in whole right side into this equation, beta 1 plus 1 over SSTX, sum from I equals 1 to n, di ui. Beta 1 hat is a constant. It is not a random variable. It does not vary. This thing is going to drop out. The xi are fixed and repeated samples, so we can take this outside of the variance function. So this is going to now be equal to 1 over SSTX squared times the variance of the sum from I equals 1 to n di ui. Now again, the di is a function of x. The x is fixed and repeated sampling. It's non-random, doesn't vary, so we can take it out of the variance function. So this is equal to 1 over SSTX squared times the sum from I equals 1 to n di squared variance ui. Now we know what the variance of ui is, right? Variance of ui is sigma squared. So we can plug that thing in there. And we have 1 over SSTX squared. Let's plug in sigma squared. What is the sum from I equals 1 to n of di squared? Sum from I equals 1 to n xi minus x bar squared. We can put the sigma squared in front because that's not part of the sum. This is total sum of squares of x. SSTX. So now we have SSTX times 1 over SSTX squared. So this is equal to sigma squared over SSTX. All right, so that is the variance of beta 1 hat. All right, now let's think about what this means. What can we interpret from this expression? The larger is the error variance, or the standard error of the regression, so the poorer fit of the model, the larger is going to be the variance of the beta 1 hat. So the farther we can expect the estimate to be from the true value. Next, the larger is the total sum of squares of x, the smaller is the variance of beta 1 hat. This is larger. This is the smaller, right? You have a larger number in the denominator, the ratio becomes smaller. And why might that be? What's the intuition there? Let's look at a plot to think about that. You have x, you have y. Let's make 2 plots. In fact, 2. Give you a 2-for-1 deal. X, y, x, y. I'm going to plot the same number of observations, one with a lot of variation in x and one with a little bit of variation in x. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so assume that here you have the same population model. From which do you think you're going to get the better fit line? It's probably data set number 2, where you have more information on X than data set number 1. Data set number 1, you have less information on X, assuming that they represent the same population model. All right, so more information on X, you're going to have a more precise estimate of your coefficient. Great. So how can we estimate the error variance? Well, we'll use a sample to estimate the population parameter. And the way that we can do this, the sigma squared hat, right? Hat to show that it's estimated. This is going to be 1 over n minus 2 times the sum from I equals 1 to n of ui hat squared. At 1 over n minus 2, because we have 2 degrees of freedom for the 2 coefficients that we have estimated. All right, times the sum of squared residuals, or the residual sum of squares. So this is equal to SSR over n minus 2. This is the way that we can estimate the error variance. Plug this into the formula for the variances of the OLS estimators for unbiased estimates of the variances, conditional on homoscedasticity. All right. And we can also use this to get the standard error of the regression. Standard error of the regression is sigma hat, which is the square root of sigma hat squared. So that's the square root SSR over n minus 2. Great. Folks, that is it for estimating the error variances. Tune in to the next video to learn some more econometrics.